Hi, everyone. Let's welcome to this edition of the ICANX Talks. And we are going to, from here, connect the world and the universe. And I'm the moderator of this session. I'm Liang Yichen from Peking University. And this month, we have already one session on Yuanling. And the next, today we're going to have Zhang Xuejun, professor from COMP CAS, and next week we are going to have Tian Zhongqun from Xiamen University. And now let's come to our speaker and panelists of this session. And we have a very strong team. The speaker from Changchun Institute of Optics and Fine Mechanics, Professor Zhang Xuejun, and I am the moderator. And we also have a very strong panelist team, Han Shen from University of Shanghai for Science and Technology, Fu Lan from the Australian National University, and we have the Grand X Challenger, Shen Hua from the Nanjing University of Science and Technology. So let's first introduce our distinguished speaker, Zhang Xuejun, Professor Zhang Xuejun. He actually received his PhD degree from Changchun Institute of Optics and Fine Mechanics in 1997, and now he is the deputy director and also chief engineer of this institute. And during all his journey, he has been engaged in many things, including optical system design and manufacturing and testing. And he had did his work, did some world-leading level of work of manufacturing, such as 30-meter telescope, Tatary mirror manufacturing project. He just handled it on single-handed. And also, as a principal investigator, he has completed a number of national research projects and won 5 national awards for achievement in science and technology. And he also received a lot of talent programs, such as Outstanding Youth Fund, and also like Qian Sunsheng Outstanding Contribution Award of China Aerospace Foundation. And he has done so many works on making better optical element and design optical instruments for aerospace and for other field as well. So without further ado, let's just welcome Professor Xuejun Zhang. Okay.
Okay. Thank you very much. Let me share my screen. I see. Okay. Thank you, Professor Chen, for your kind introduction. Can everybody hear me? Okay. So I say good evening to everyone. My name is Xuejun Zhang. I'm from Changchun Institute of Optics, Fine Mechanics and Physics, Chinese Academy of Sciences. First of all, I want to thank the ICANN talk organizer, Professor Alice Zhang, for extending to me such a good opportunity to give this talk on ultra-precision optical components manufacturing and metrology technology. And I myself have been involved in optical system design, fabrication, and testing for more than 25 years. And optics is fantastic to me. Before we get started, I'd like to spend a few minutes to give a brief introduction to Changchun Institute of Optics and Fine Mechanics and Physics. I think there's something, I think I have to, yes, here we go. Let's see. This is a very brief introduction to the CIOMP. And actually, the name is very long and it's difficult to pronounce CIOMP. So you can pronounce the name as SIOMP. Okay. So here is the map of China. You can see here is the location of Changchun. We are located to the northeast part of China. And here is Beijing. They're about 1,000 kilometers from here to there. And we were founded in the year 1952. The founder is Professor Wang Dazheng, who was one of the most prestigious professors in China. And during the 70 years history, we have been helping establish several other optics institutes in China. Like, for example, the Anhui Institute of Optics, Shanghai Institute of Optics, Xi'an Institute of Optics, and as well as Chengdu Institute of Optics. So we also call the Mother Institute of Optical Industry. And during the history, we have created many China first, and we can we came up with the first theodolite, the first microscope for the industry use. So we are doing a lot of pioneer work to China modern optical industry. So there were 23 researchers from SIOMP have been elected as academician of Chinese Academy of Sciences or Chinese Academy of Engineering. And this is a new working area. We started operation in the year 2003. So up to 2020, and we have totally 2,025 employees. Among them, there are 291 research professors, as well as 700 associate research professors. So this is our main research areas, include luminances, applied optics, optical engineering, and precision mechanics. So you can find applications in energy, space, industry, and astronomy as well. So the last fiscal year and the total R&D funding is $600 million US. I should say 85% of the money are coming from the competition. As a major optical instrument supplier, CIOMP can offer component or system level solutions, including space optical payloads and DUV lithography optics. Okay, so this is the outline for today's talk. And we'll start off some background information about the current space telescope and some ultra precision optics for lithography industry. And then I will talk about the recent progress in the silicon mirror technology at SIOMP. And after that, I will talk about the ultra precision manufacturing and testing for lithography optics. And finally, I will give some comments on the recently popular robot polishing equipment. We'll talk about some advantages and disadvantages. By the way, as I know from the last, the previous ICANN talk, like I understand that most of the talk are science oriented. So you could find in my talk are more engineering and technology intensive. So I hope the material presented here can help you to bridge up the gaps. And also I will try my best to make it interesting. So as we know, the optical instruments are essential tools for exploring the world, including the universe study and everyday life and the micro world. And ultra-precision manufacturing and testing are enabling technologies for the industry sectors, including space or ground-based telescopes, Earth-observing satellites, EUV lithography optics, and etc. And this view graph will show the recent development for telescopes and the lithography optics. You can see from the picture, the aperture and the accuracy of aspherical elements is gradually improved. And also the spatial frequency for the surface error should be well controlled. This is very critical, especially for EUV lithography optics. I will address that later. So this table, they gives the requirements for the optical components for different industry sectors. And telescope, for example, the space telescope, now the largest one is a Hubble, is a 2.4 meter in diameter. Now they are building some future plan, which is 4 meter diameter. So the accuracy is from 10 nanometer to 4 nanometer for the figure error, and 1 nanometer through 0.5 nanometer for the high frequency stuff. So the accuracy, aperture and accuracy ratio has been to 10 to 8 to 10 to 9. While for EUV optics, the aperture size is ranging from 0.1 through 1 meter. And you can see the accuracy from 0.14 down to 0.05. It's almost 2 magnitude tighter than the telescope optics. And also the aperture accuracy ratio has reached 10 to 9 to 10 to 10 level. So this is a really strict demanding for this industry application. So this is a painting I can find in Jena, Germany. They are one museum called Jena Optics Museum, and the painting, they just illustrate the old-time optical workshop. And from a picture, you can see this druggist guy is polishing or grinding the optics, and the other guy is checking the quality, and this guy is maybe observing and testing the whole telescope. And this old man, it could be instructor. So nowadays, those processing chain is still similar. The thing is that the hand polishing is replaced by high-level CNC polishing machine, and the observing testing equipment has been replaced by the laser-based visual interferometer. But the whole process is still the same. You need start off design, then you go through grinding and polishing, then metrology, then observing, assembly, and testing. So for your students who have been involved in optical engineering, then you can use this picture as a reference for looking for job. For optical fabrication, so there are two main directions. One we call the super large aperture optics, and then we have an example for the space telescope under construction here at Xuejun is a CSST. It's a 2 meter off-axis design. I will address the manufacturing issue for this telescope. And the other direction is the ultra precision direction. One good example is the EUV lithography optics. The card size is the state of art, and I will address some metrology issue also later on, okay? So for the space telescope, we say the primary mirror diameter is still a dominating factor for large telescopes because based on Rayleigh criterion, the resolution is proportional to the diameter, and the light collecting ability is proportional to d squared, while the cost is proportional to d cubed. So we still need a large aperture to collect more light and to give us a good resolution, but that also spend a lot of money to build such a large telescope. And if you look at the other community, we call the Earth observing optoelectronic devices, you can see from this table that the recent launched operate space camera, they are resolution are getting higher and higher, and the normal frequency, the normalized frequency is also getting higher. So what is the normalized frequency? So we know the optical system has a cutoff frequency is equal to lambda over 1 over lambda times F number. But the system is still a undersampling system because your CCD is sampling somewhere here, but your cutoff frequency for your optics is somewhere here. So the system is an undersampling system. But nowadays trend is the normalized frequency is getting close to the cutting off frequency. So the system is close to standard sampling. So what does that mean? We say the high normalized frequency will give you a very compact design. This is a very good news for space application because you save a lot of weight and room. This is a very cost-effective way of designing your payload. But meanwhile, it gave you tighter tolerance for your optics. The reason is you have less room for your optics when you get the standard sampling system. So you can see from these two pictures, one is called the Rayleigh criterion. It says that if the system wavefront peak to valley error is less than lambda over 4, or the Materiality criterion that says if your RMS WFE is less than lambda over 14, the system is working under near diffraction limited. But for high NF system, you also need to worry about the middle or high frequency stuff because they will spread the light out of your center region of their PSF, so they cause the lower contrast for image. So this is very important for high NF design. So I'll address that later. So, but for astronomical telescope, you can see the recently planned telescope. They have a similar resolution as Hubble, which is 0.1 arc second, but the field of view is much larger. Take Chinese CSST, for example. The field of view is almost 200 times greater than Hubble. So the reason we get that result is for Hubble is on-axis design, and so you have so you have a central obscuration here, and you also have the spider, which is supporting the secondary. They cause the second diffraction. So the image is like this, but in our design we are using off-axis design. So you don't have an obscuration, so the PSF is very clear. So that will help you to get a large field of view. And here is the design result. You can see you can see both the ellipticity and the wavefront error can be improved by a factor of 2. So this picture showed the optical telescope assembly and also the outer bar assembly. So if you compare the size with the minibus, you can see this is a really huge telescope. So this picture, they show the evolution of the optical layouts. And you can see the design freedom is increased, while the complexity also increased. And the Hubble is a two mirror system. It's a rich gradient system, while the Worldview 2 is on-axis TMA, is called quartz TMA. And also in 2000, we launched a lot of off-axis TMA system. And in 2010, we started freeform design, and we launched in 2016 Chinese GF6, which is a 4-mirror freeform off-axis design. So we get the field of view increased by a factor of 3. So this is an evolution of the optical layout. So what is freeform? Actually, the freeform surfaces, they originated from A-sphere. So Professor Zhang, he has a very good comment in his book, The Fundamental Theory of Optical Design, published in 1965. And he said that A-sphere is equal to a sphere plus a Schmidt corrector without any optical power. So the benefits of A-sphere surface is they give you more design freedoms, but still same Seidel aberrations. And also they can reduce the number of the elements and improve the performance. So you can see a lot of lens are used for lithography optics. And if you replace the spherical surfaces with the aspherical surfaces, you can reduce the total number of the lens. So that is very important for the lithography system like this size. Okay. So the freeform, and we're talking about for imaging optics, is still based on the A-sphere. For example, the conic surface, then plus some non-symmetrical polynomial terms. Then those terms can be either Wernicke polynomials or XY polynomials. Then you have some other options. And recently, the Forbes proposed a Q-tap function, which is also Wernicke based, but is orthogonal, a gradient orthogonal Wernicke polynomial. They can better describe the shape of the surface under discussion. So this is you have many choices. But here in our case, we choose the Wernicke polynomial because this is a well understood for optical designer and optical testing, and as well as the opticians who work in the shop. So we just choose the Wernicke polynomials to add it on our base surface. Then we'll create a lot of good result. So how the freeform surface behave? When you have a large oblique incident ray on your rotational symmetric surface, you have a kind of what we call the astigmatism aberration. That is because the surface has different optical power in the two orthogonal directions. One is in, we call the tangential direction, the other is the sagittal direction. When you have this oblique ray incident on the surface, you have a different power, so you got astigmatism aberration. So if we use a anamorphic or freeform surface to replace this rotationally symmetric surface, so they will zero out at least for one incident angle, the astigmatism. So that is the basic function for the freeform surface. So Professor Roland Schack in University of Arizona, he came up with the what we call the nodal aberration theory that well describe the behavior of the off-axis design in your optical system. And for freeform surfaces, they can create two 0 point in your field, which is astigmatism free. And for Zernike surfaces, this node are known as are known and designable. So that's give you a lot of freedom to choose the different surfaces. So that is why we're using a freeform surface in our design, because they can increase the number of the points in the field where astigmatism is 0 relative to the rotationally symmetric surfaces. This is a very big advantages. And also the unobscured mirror design, which inherently high oblique reflecting angle, are well suited to use the freeform surfaces. So we see the nodal strategy are even more effective in this high order design of the system. So this is two pictures. They show some design result by using the conventional off-axis conic section, and the one who used the freeform optics instead. So you have a compact design result. Also, the imaging performance is much better than traditional one. So in summary, we still need large mirrors for space telescopes, but the aperture size has increased from 1 meter to 4 meter, and the surface type has been becoming more complex, even including freeform mirrors. And the requirement for the specs of the system with a high normalized frequency, you need to control the low and middle and high spatial frequency residual errors, 7 nanometer RMS and 1.5 microradian slow power RMS are becoming popular. So the commercial electronic satellite, they use cost-effective design. They need more affordable space qualified optics. So those new trends just challenge our current existing technology. So we need some breakthrough in current technology. So how to make the large reciprocal mirror in cost-effective way? We need first to choose the right material. We call this the high performance material for the mirror blank. And I can show from this table the several space qualified material ranging from the URE, Zero, and beryllium and silicon carbide. And we compare their mechanical and thermal property by means of specific stiffness and thermal conductivity. The specific stiffness is defined as the elasticity divided by the density. The higher, the stiffer the mirror is. And by comparing the silicon carbide with the traditional URE and Zero, you can find the specific stiffness is higher than the traditional material by a factor of 4. That means you can have a very lightweight design, but still keep the good stiffness. As for the thermal conductivity, the silicon carbide also has a very good thermal stability compared to the traditional material. So these two features make silicon carbide a very attractive material for space telescope mirror blank. So silicon carbide mirror has a heritage in Europe and in US. You can see from the pictures here, they show the Herschel telescope, which is 3.5 meter silicon carbide, but it's not working in visible light. It's working in the microwave, so the accuracy is 3000 nanometer in RMS, almost 2 magnitude lower than the visible light applications. And the other famous one is a Gaia, is a 1.5 meter by a half meter, also off-axis design. Then Aladdin is another one, so it's a 1.5 meter. EO1 is a silicon carbide telescope built by SST, the American company. All those space telescope using a silicon carbide mirror, they show a good performance. So here is some example in CIOMP, and we're working on 2 meter and 4 meter telescopes. And you can see this is a primary mirror for the Chinese Space Telescope. If you compare this with the Hubble 2.4 meter mirror, and you can see the weight is reduced by a factor of 2. That should thank for the excellent thermal and mechanical property for silicon carbide material. And also, if you look at the Sophia is a European project. The primary mirror is a 2.7 meter and 0 dual. And also, you can see the light weighting structure is by mechanical milling process, and the area density is also two times heavier than the silicon carbide. Well, with our technology, the near night shape is casted, so you don't need the complex light weighting milling process. That's a low risk and a cost-effective way of making such a big mirror. I hope, my friend from Schott, you agree with me, and because I know in Europe, people love 0 dual more than silicon carbide. Okay, why we use the reaction bonding technique? Because the reaction bonding, they can cast the green body into the near night shape. So you have a low risk for the shrinkage. And if you compare this with the sintered process, you can see the sintered process, the green body is pressed into a disc. Then you use the mechanical milling process to do the light weighting, and the shrinkage is greater than 15%. So if you want to make a large mirror, you have a high risk for cracking and deformation. So that is the reason why the reaction bonding process can produce a meter. The size is greater than 2 meter, and the largest one ever made is a 4 meter. So just finished in the year 2018. And the other benefit is with the reaction bonding process, you can make the semi-closed spec structure. So what does that mean? If you have a mirror with the same size and same thickness, but one is an open back, the other is a semi-closed back, so you get the stiffness increased by a factor of 2. So this is a very good news for space application, because we need something light and stiffer. So this image, they show the evolution of silicon carbide R&D process. We start off 2008 by making 0.5, 0.6 meter size. Sorry. And in 2016, we were able to make a 2 meter size. And recently, we just finished a 4 meter size mirror. And our manufacturing equipment also improved during the past 10 years. And you can see this is the first generation machine. This is all CNC box machine. And the aperture size is from 0.5 meter to 2 meter. And accuracy is about 16 nanometer to 30 nanometer. And since 2003, and we started a new investigation on the series of computer-controlled optical surfacing and stress-like polishing and MRF finishing and IBF finishing machines. We built in-house a series of those machines. The aperture size increased from 100 millimeter to 4 meter, and the surface error can be controlled from 20 nanometers to 7 nanometers. Okay. And here is one good example. For the old technology, and we begin with the best fit sphere, and then we use C-cos grinding technique. Then the mirror goes through pre-polishing, then they go through the silicon overcoating, then the final post-CCOS polishing. The processing time is about 24 weeks, and accuracy is 12 nanometers in RMS. But with our new process, and we direct cut the mirror into the A-sphere shape, then they go through CCOS grinding and pre-polishing, and then the silicon overcoating. Then they go through MRF polishing, then ABF polishing. You can see the final accuracy can be better than 7 nanometers in RMS. The total processing time is only 10 weeks. So processing time is saved by about 60%, and the accuracy is improved by 45%. So this is very mature for the 1 meter size mirror fabrication. But what about the mirror getting larger than 1 meter? For example, 2 meter, 3 meter, or 4 meters. And let's look at the processing chain. And we begin with the silicon powder, and we make the blank. Then they go through grinding, polishing, and final finishing. Then you end up with this shining mirror. So this is a basic processing chain. What is happening here, if you look at the 4 meter aspherical mirror, they have, say, peak to valley departure is 20 microns. And if you have a 1 meter size mirror with the same PV departure, and the total material removal cube for the 4 meter mirror is 1 times 10 to 5 cubic millimeters. And for the 1 meter size, it's only 8 times 10 to 3 millimeter square, millimeter cube. And if you look at this differences, we say it's 16 times more materials should be removed. And if we use the same strategy for the 1 meter fabrication, it used to be 6 months. And the 4 meter mirror polishing, they need 8 years. That is unacceptable. If I tell my boss I need 8 years to finish this mirror, I will be killed. Okay. So we need some essential breakthrough for the manufacturing technology on large mirror. So let's go back to this processing chain again. The first step to produce the mirror is to generate a basic shape. Traditionally, people will cut the mirror to the best fit sphere. And from that point, they start a large tool lamping. And for the, we have a example for 1/2 meter A-sphere. And if we do from best fit sphere, and the removal cube is 1.2 times 10 to 6. If we direct cut the mirror into the A-sphere, and say the accuracy is something around 20, 30 micron peak to valley, and the material removal will be 4 times 10 to the 4th. It's reduced by almost 2 magnitude. That means 30 times less material will be saved. So the lamping time is greatly saved. So this is a very a good strategy to work on the large aspherical mirror. But the one thing you need to take care of, that is the tool wear, because the silicon carbide is a very hard material. You use the diamond wheel, then for the cutting process, you have to think about the tool wear, and you have to measure and compensate in your cutting program. So after compensation and the peak to valley for the 1/2 meter mirror can be better than 10 micron and peak to valley. So that is a very good start for next lamping process. And this image shows the process of cutting the aspherical mirror up to 4 meters. You can see with the two composition, we reach something around, say, 17 micron in RMS on 4 meter mirrors. So this is a pretty good result. Okay. And after generating, and you need a large tool grinding and lamping. If you use a stiff tool, you don't have a good fade. That means that this spherical surface, the local radius curvature is changed point by point. So if you don't have a good fade, you will leave a lot of middle frequency stuff. So one solution is to deform your tool to make it conform with the local curvature. So we call this a stress lap tool. So if you use the stress lap tool, then you can have a good removal while keep middle frequency well controlled. So here I will show some real polishing example on the 3 meter off-axis mirrors using the stress lap tool. So after lamping, and the surface is almost better than 100 nanometer, but one problem is for silicon carbide, you have a two-phase material. If you look into the microstructure, you can see the silicon and the silicon carbide is a two-phase material. So if you use this bare surface for visible light, you've got a lot of scattering losses. So one technique called overcoating technique is employed to overcome this problem. Basically, we use the PVD technology to overcoating a thin layer silicon on top of the surface. Those defects will be covered up. Then we polish the silicon layer and with the MRF or IBF tools. Then we end up with the optical quality surface, which is qualified for visible light applications. This is the whole idea. And so here is the example shows the large MRF tool working on the silicon overcoated surface. You can see this is two influence function, and they have a very good convergency on the high frequency stuff. So if you use a small MRF tool on the large mirror, you also have the efficiency problem because the removal cube is about a 8 millimeter cube to the third. So if you use the small tool, and you need almost 24 days. And we changed this MRF wave from 160 to 360. So the total process time will be finished within 4 days. So this processing time is reduced by a factor of 6. So this is a great improvement. You may realize something on the large mirror is different from the small mirror polishing, because from this picture you see a 2 meter size mirror. You use a different approach, like small tool, CCOS, MRF, and stress light, and the tool size and the shape are different. So you have a different influsion functions. We call the tool influsion function is TIF, convolve with the dwell time. They give you the total removal. But in our practice, we know the expected removal by measuring the surface, and we know the tool removal function by testing each tool influential function. And the question is how we get the dwell time. And mathematically speaking, this is a deconvolution process. But if you have a different shape of the two influsion function, that means the deconvolution model doesn't fit that. Here we do some little math. We turn this convolution process into a matrix products process. So in that case, you can insert all different two influsion function into your removable matrix. Then you can do the inverse matrix operation to get the dwell time. So these two pictures show two different computing results. You can see by parallel computing the dwell time, you get a very good residual mag. Here is some result. This is a 2-meter mirror finished with an accuracy 12 nanometer in RMS. Whole processing time is 12 months. And meanwhile, we have a backup mirror made from Zero, made in Belgium, a company called Amos. They end up with something like a 23 nanometers. They're using very small tool to polish this, but you can see a high frequency stuff over there. And here is an example of the large MRF working on the 4-meter mirror. You can see the convergency of the high frequency stuff. Okay, the other part I want to talk about is the metrology of the large mirror, because as you know, you can't make optics any better than where you can measure optics. To measure the large spherical mirror, you have to take care of the gap from the micrometer accuracy to the nanometer accuracy. The dynamic range for the single device cannot cover that. You have to take care of the air turbulence, mechanical vibration, and self-weight deformation. And here they show the problem with the Hubble. As you know, the Hubble is a 2-meter two-mirror system. The primary mirror and secondary mirror are all made from ULE, and the shape is hyperbola. And when they launched in 1990s, they didn't get a clear image at the first light. They checked back the problem, and they found the null length for testing the aspherical surface is wrong. By the distance error is only 1.3 meters. So this causes a 1 lambda spherical aberration on the surface. So to beat that problem, and they choose the Costa program to fix Hubble. The basic idea is to make a corrective lens. The accuracy is better than lambda over 100. Then they use the astronomer to do the operation outside the space and to repair the Hubble telescope by insert those corrective lens in front of the image plane. Then the Hubble can look back. So here is the result before and after the fix. And after that, people realized that the expensive primary mirror must be cross-checked before launch. So you use a null lens, then you use something to test your null lens. Here we came up with the, we call it computer-generated hologram, which is made by means of laser writing or E-beam writing. It's a totally different technique. Then they use this one as a ruler to test your null lens to make sure the spacing and the positioning are correct. So this will guarantee your primary mirror never make mistake. And for JWST, which is to be launched in 12 December this year, it's a deployable mirror. The size is 6.5 meters. And NASA learned a license from Hubble, so they built a 6.5 diameter collimator to test the whole telescope. And but JWST is working at the near infrared, so the accuracy requirement is only 60 nanometers in RMS. Not like a visible light, they need a 10 nanometer accuracy. So for side arm solution for testing such a large mirror, we're using a swing arm for the grinding stage. And actually, the Dr. Jim Birch from the University of Arizona, they first came up with this idea. Here we do some modification. We built this rotating table into our fabric polishing machine, so they can give you a benefit for in-situation measurement. You can see the good agreement from the swing arm testing and the interferometer testing. This is for supporting system to overcome the light self-weight deformation problem. And here is a testing tower. You can see the CJs is right here, and here is the interferometer. It's looking down to the surface under test. And this is a live video to show the testing process. You can see air turbulence over there, and we have our software and to decouple this effect, then you have a stable testing result. That's important to get you through the full final polishing. Well, this is the mirror finished for 4 meter acyclical mirror. The accuracy is better than 50 nanometers in RMS. This is also largest silicon carbide acyclical mirror ever made in the world. So here's another piece. It's a 3 meter off-axis acyclical mirror, and the final accuracy is better than 30 nanometers. It's also the best one ever made. And this is CSST current status, and the OTA is under assembly. You can see the huge truss over there, and you can see the primary mirror is almost finished polishing. See the nice straight and equally spaced fringes. Okay, so we finished part 2, and to celebrate that, I have a sip of tea. So let's move on to ultra precision manufacturing testing of lithography. So from this equation, you see the frequency lower lambda down and NA up, and the K1 down has been repeated several times during the last 25 years. So this equation is came up with by Ernst Abbe. It tells us the dominating factors for the resolution for microscope. And the car size is state of art right now. So they show this picture. They tell us we have to control both the figure and roughness. In the roughness, the most serious problem is caused by, we call the middle frequency, spatial frequency roughness, because they cause the light scattered still inside the field of view, because your CD unit is affected. So it just directly lower your resolution. So you have to be taken care of for the middle frequency staff. So why we need such a picometer accuracy? From those equation, and they can do some simple mathematics exercises. Then you can find for DUV, the working wavelength is 193 nanometer. And for the EUV, the working wavelength is 13.5 nanometer. So this is a big difference. So if you do this calculation, you can find the figure error tolerance for EUV mirror is 20 times tighter than that of the DUV surfaces. And for the roughness, and both the middle spatial frequency and high spatial frequency is dominated by the straight ratio. And if you look at this simple equation, then do some simple math, then you can find that the amount of the straight light of EUV mirror is 3,000 times larger than the DUV lens surface with the same surface roughness in RMS. So that is why they need picometer accuracy for the EUV optics. And for the mirror, you also need to think about the manufacturing residue, gravity deformation, assembly and adjustment error, and design residual, coating error, and thermal effect deformation. So all this error budget together, according to the Marisol criterion, lambda over 14 is not enough. For the single mirror, we need the whole system wavefront error should be better than lambda over 50. So that means that EUV lithography systematic error should be better than 270 picometer for each individual mirror. By the way, it's a 6-mirror system, should be better than 55 picometer in RMS. Then for measurement requirement, the repeatability should be better than 12 picometer in RMS, and the reproducibility should be better than 20 picometer in RMS. So this is a very strict demand. So this picture, they show the processing sequence for EUV optics. We start off grinding and C-coat polishing, IBF figuring, or coating. Then you can see during this process, we do surface measurement and also the roughness measurement. Indeed, the testing runs through the whole manufacturing process. So we have to take care of the measurement. There are two aspects you need to be realized. One is the precision. That means the repeatability plus the reproducibility, because you have to test your mirror and then you have to test and then you have to polish and test. Is an iterative process. So the result must be reproducible. Also, the other aspect is the accuracy. They determine the success or failure of your system. And here we show one example for the Xuejun polisher to polish the mirror and test under the normal pressure. You can see the accuracy is fluctuate around 3 nanometers. That means with the air turbulence and temperature gradient, they cause the unstable testing result. To overcome that problem, you can make all your test setup in the vacuum chamber and also with the vibration oscillator, and the environmental temperature should be controlled better than plus minus 0.0 K. So this is a approach came up. I think it's an approach in the car size. So they're practicing all the testing in this vacuum chamber testing station. And for accuracy, one of the big error sources is your reference surface. So you can choose to use what we call the point diffraction interferometer, which use a spherical mirror diffracted by a small pinhole that could be taken as a perfect reference. But that one is only suitable for testing spherical surface. What about the A-sphere? For A-sphere, then you can use the this is a dioptic company, it's a German company. They came up with an innovative CGH design. They just improve the reference accuracy by empty the visual cavity. So this is a pretty smart idea. So for the CGH itself, it can do a lot of calibration work to cancel out like power, wedge, and angle. After doing those calibration, then you have a very good accuracy to meet the spec requirement for the EUV optics. So here we make a lot of CGH at Xuejun, including both amplitude CGH and the phase CGH. And finally, I want to talk something about the box machine and the robot machine. The motivation of doing this is during the work on 4-meter mirror, we found Large aperture complex surface require high stability and efficiency of the manufacturing technology. And a CCOS plus MRF have proven to be a good solution. And to apply this technology to mass production of 1 to 3 meter, 1 to 2 meter surgical aberration, we need some modification. For example, the ground-based telescope under construction are reaching 30-meter level. For example, the European extremely large telescope, they are segmented mirror altogether is nearly 1,000 pieces, plus the spare blank altogether will be more than 1,500 pieces. Each one is a 1.5 meter off-axis focal mirror. If you use the box machine, it works fine, but they have some problem. They are expensive. When working on large mirror, they need a big machine to occupy lots of room. It's not good for mass production. And in situ measurement is difficult because it is in box, and your remount takes time and reduce accuracy. What is the advantage for robot? It's less expensive, it's safe spacing by a factor of 3 or 4, is suitable for mass production. And meanwhile, it's open, so you have an in situ measurement possibility with both interferometer or diffractometry. And the robot is good, but we still have some problem because the robot 3D trajectory is less precise compared to the box machine. This results in the variation of your two-influential function. You have options to overcome this by either customize a high accurate robot controller, but this is not recommended. This is expensive. You can monitor the attitude by laser tracker and compensate in software. Well, we can do that. One can do a test run and take the result as an additional error and polish in the next test run. So this is also a possible solution. Or you can use a SciAmp robot adapter. It's a patent pending technique that can help you to overcome this problem. Here I have some examples of the robot together with the small tool polisher. Here you can see the MRF wheel with the adapter. And our software can help you to calculate the tool paths, either raster or spiral and random, or you can do measurement and data handling, including distortion correction. And you can merge your data from different sources, swing arm, IMRF, or interferometer or diffractometry. You can calculate the dwell time by either deconvolution or forward calculation. You have many options. It's a very powerful software. Here is some result for the real mirror polishing. You can see for 1 meter by 470 millimeter silicon carbide off-axis mirror, they can polish to the accuracy better than 20 nanometers in RMS within only 1 run, 7 hours polishing. And here is an example to use the diffractometry together with this robot polisher. It's a very effective way monitoring and also assisting the MRF polishing process, especially when the interferometry test is not available. So here it shows some real-time result. You can see you can do the online real-time measurement. This is a benefit of using diffractometry. And here is the example, and it shows the convergency of the 1 meter mirror. We start off with a peak to valley 1/2 meter, 1/2 wave. RMS is 0.15 wave. We end up with the RMS is better than 0.027 wave. It's almost as good as the box machine polisher result. And another nice thing about the robot is it's more agile and flexible. That you can go either the traditional two paths. You can also go as a very random two paths. And what is the benefit of doing that? Then you can compare this result. They're all better than 7 nanometers. And if you look into the detail, you can see the random paths, they cause some additional frequency stuff, while the raster two paths, they have a more regular two paths. We're still working on the detailed study and optimize the two paths process. The work is still underway. Well, if we use our robot to polish the EERT segmented mirror, and for example, if you use a 50 robot working simultaneously, and if you do the calculation, you'll find all the 1,500 mirrors could be finished, fine polished within 7.5 months. Well, that sounds a good deal. That's a very good process compared to the box machine. So where we buy those robots? Well, we have a lot of spin-off companies, and you can find the solution, either the box machine or the robot machine, and also the silicon carbide materials. And you can check their website to do that. Okay, to summarize my talk, and the CIOMP could deliver a complete solution of the large silicon carbide mirrors from blank to fine polishing. The direct generation aspherical shape save processing time by a factor of 2, and the CCP combined with the MRF polishing has proven to be a reliable way to make high-end large silicon carbide mirror. With in situ figure testing method for different stages, including a swing arm and vertical CGS interferometry, better than 16 nanometers RMS for 4-meter aspherical mirrors can be achieved. And the robot-based MRF is a promising approach for cost-effective mass production of high-end large aspherical mirror fabrication. Okay, thank you very much for your attention. Thank you.
Thank you, Professor Zhang Xuejun. It's really a eye-wide open experience. I must say, it's really actually fits our let me see. Let me share my screen. Fits our goal of connecting the universe, connecting the world and the universe. That's actually our world and the universe above, right? So it's really interesting. So without further ado, let's introduce our panelists and each one of our panelists and before discussion. So first is Professor Hansen, and he actually graduated from University of Stuttgart in Germany, and also he has I think he's a co-founder for instrument company and won R&D 100 award twice in United States, which is quite some achievement. In addition to the publication of over 100 papers and over 40 patents. So he's actually now in University of Shanghai for Science and Technology. Oops, I should display. And the next we will have our very beautiful panelist, Professor Fu Lan from the Australian National University, and he is also the head of the Department of Electronic Material Engineering at the Research School of Physics of ANU, and her major research including design, fabrication, and integration of of optoelectronic devices such as LED, lasers, photo detectors, solar cells, and all other stuffs. And also she had published over 200 papers and many book chapters or conference proceedings, as well as serving as program committee on the symposium chair for many conferences. So, and one thing I need to mention that is Professor Fulan was the recipient of the IEEE Photonic Society won the, as a graduate student, won the fellowship, and then the Australia Research Council postdoc fellowship, and then the ARF fellowship, and then the future fellowship, and then the distinguished lecturer award of the IEEE Photonics Society. So you can see she actually started as a graduate student from IEEE and ended also there. It's a perfect circle. So she's also now the Australia Academy of Science National Committee on Material Science and Engineering and all other honors. And finally, we have this session of ex-challenger Shenhua from the Nanjing University of Science and Technology. And he actually got his PhD of optical engineering in the same university, and then visit University of California, Los Angeles from 2019 to 2020. His interests mostly focus on optical precision metrology based on Interferometry, especially on the complex surface measurement technology. So he's the perfect guy to make the challenge today. And then with all the people have been introduced, now we come to the session of panel discussion. Okay. And usually we start with the youngest one, which is the challenger, our grand challenger.
Thanks, Professor Chen, for the introduction about me. Just now, Professor Zhang gave us an excellent talk about ultra-precision optical manufacturing and measurement technology. I got a lot of useful knowledge and information from his talk. Today, it's my great honor to be here as an ex-challenger. Now, I have two questions. The first one is, as we all know, with the rapid development of the technology, there is a trend that the precision demands of the optical manufacturing is going to be over the limitation of current measurements accuracy. Professor Zhang, what new measurement methods do you think, based on novel idea or theory, could be applied to break the limitation of current measurement accuracy? This is the first one question.
Okay, so you have two questions. I have to answer one by one, or you just read out all the questions and I will answer them all together.
Okay.
Yeah.
What is your second question?
My second question is, in order to improve the resolution of space observation, the aperture of the optical observation system is larger and larger. How do you think the proposal that using computational optics method to improve resolution as well as reduce the diameter of the aperture? Thank you. This is my second question. Okay.
Okay, thank you. For the first one, well, is there any other brand new measurement technology could be introduced to improve the testing accuracy? As far as I know, people came up with some idea like point diffraction and interferometry, which is an excellent idea for measuring the super high accurate optical element. That one has been commercialized, and also in our lab we have in SciAmp, we have using this technology for measuring the super high quality optics. But for the A-sphere or freeform surfaces, you still need some Nodal to transfer your spherical aberration, spherical wavefront into a freeform or aspherical wavefront. So that one cannot be avoided. It's inevitable to use the Nodal element. So the question is, well, if we can find some way to make a zero aberration Nodal element, there could be a better way to solve this problem. So we're working on that by using some EV writing process instead of laser writing process to make a high accuracy CGH. Also, you need the design from design aspect. You need some physical optics computation capability to help you to find out the small feature induced error. So this is also an important thing to do. For your second question, I think the computation imaging is a promising technology. We are using this new technology to improve the image performance of our own products. That's no problem. But the thing is, we are still working under the framework of the diffraction limited. So we still need large telescope because for the astronomy application, for example, you are looking at some very faint object. You need a capability for collecting more light. So you need to enlarge your aperture. From this perspective, I think the new computation imaging technique, together with the traditional large mirror fabrication technique, they will generate some we call it smart camera, and they can help you with a good image quality as well as the excellent light collecting ability. So this is my understanding of the question. Okay.
Thank you. That's very nice. How about Professor Fu Lan? Do you have some questions?
Okay. Thank you very much, Professor Zhang. That was a very impressive work. My question is a very general one, actually. When you talk about the technology for the space telescope involved from two mirror system now to multi-mirror system. So what can I understand is that when you have multi-mirror system, you can have more compact system. In addition to that, what actually advantage in terms of improved resolution by having a multi? Can you explain what is the extra advantage that having a multi-mirror system will offer?
Okay, thank you, Professor Fu. Actually, people are using a large aperture, but it's limited by the launcher shoulder size. So the JWC, for example, the launcher is only 4.5. So their aperture is 6.5 meters. So they have to fold the mirror before launch and deploy this as a whole segmented mirror in the space. So this is a technical problem. They have to do that. But the difficulties is when you deploy them in the space, each segment should be finely aligned and to make the pieces working as one. So we call this co-facing technique. So the accuracy used to be better than 10 nanometers. So you think about this for a second. You have more than 100 pieces of such a 1 meter pieces. Each one should align to each other to the accuracy of 10 nanometers. It's a very difficult technique. And also you need a reference to tell you, to get you through this process. In space, this is even more difficult not like a ground-based telescope. You can find a lot of known star as you're getting started to do this. So that is the difficulties. But once you overcome those cold-facing problem, eventually you have a larger aperture telescope. They give you better resolution than 2 meter, 3 meter. So then if you have overcome all this problem, you can expand from 6.5 meter to even 10 meter or even larger. So, okay.
Okay, thank you. And yeah, Professor Shen. Yeah. So how about a question from Professor Han? Sorry, Shenhua. Okay. Professor Han. Professor Han.
Okay.
Sorry. Yeah.
All right. Okay. So great. I think Professor Zhang, you did great job. I think that's great presentations. You know, which you know I learned recently. So I think I don't know what question I should ask you because you did perfect presentations. But you know, wait, I still have I still have some. You know, first of all, the 2 comments for you.
Okay.
So number one, I think the fabrications and the testing, I think that both are like a twin, right? So you did both optical fabrication and the testing. So that's great. So the number 2 of the comments is for large optics and the lithography. You know, this is the large optics, probably you are using the light, the visible light, right? And lithography, you use EUV or UV light. Is really the short wavelengths. So this is like from optical point of view, this is you know, like a both end, right? One is large, another one is quite small. So just this is you know, the 2 comments, you did a great job. But following the second comments, I think I still dig out some questions for you. Okay. So the number 1 is, you know, since the EUV or UV is a short wavelength, you know, it's like you mentioned, it's a 193 nanometers, or another one maybe, you know, 13.5 nanometers, right? So for the large optics, because you need the more and more accurate the large optics. So what do you think is can we also use the short wavelength, you know, in order to test the high accuracy of large optics? So that's the number 1 question.
Okay. Well, that's a good one. I understand that you're asking whether or not we can use the short wavelength as a light source to measure the optics working in EUV or UV. Well, it's quite possible because someone are practicing this, and I know in somewhere in the world. But the thing is, if you use EUV light source to test optics, you have to do it in vacuum, because when that short wavelengths will be absorbed by all the materials. So you have to use a test, maybe use test setup inside the vacuum, where you have to make everything vacuum qualified. So that costs a lot of money. That's the one thing. The other thing is you have before you coat, you mirror, the normal incidence will be very low for those short wavelengths. So during the polishing process, and this is not suitable technology for measuring the mirror using that short wavelengths.
So it's hard.
But you can do it to measure the whole system. When you finish assembly, then you have to use the working wavelengths to measure the whole system. That will tell you what is the defects. That is a must-do job after you assembly the whole thing.
All right. Okay, thank you. The number 2 questions. So since you try to measure the spherical surface, right? So you may either use compositor or CGH. So my question is, in what case, or how you can figure out in what case you would like to use the optical compensator, and in what case you would like to use the CGH, and also how you can calibrate either one.
Well, that's a good question, and just ask expert question. Okay.
Thank you.
Because actually, for the old time, people are using no lens a lot more than CGH, because at that time the difficulty to make a CGH is so big and so expensive, and but nowadays I think the CGH is not that difficult to be made. So you can find a lot of suppliers. Even Scion, we make our own CGH by a laser writer process, and so I think in our case we use 90% of our testing elements as a Nolan as a CGH, but there's some specific case where your mirror is big and the departure from the best fit sphere is large. Then you have a very large caustic. Then if you use your CGH, the CGH must be located far from the caustic. That means the size of the CGH is very large. Actually, the current limit is something 300 millimeters in diameter. So if your caustic is better than that, is larger than that, you have to think about the compensator, or you can use compensator together with CGH.
Oh,
to help you to solve the problem.
That's great. That's great. And the next one is how to calibrate, either one.
Yeah, for the compensator, then you can use the CGH as a calibrator to calibrate the compensator, because the CGH can be more accurately made. But for the CGH itself, you have to use a different design to cross-check, because as I said, you have caustic, then you have many positions to be chosen to place your CGH. Then you can have a different design and two pieces of CGH located at a different position. Then they cross-check each other, and they will tell you what is wrong with the CGH itself. That could be a way to do it.
So you cross each other, the check one by one, right? So
yeah.
Okay. Very good. So the last one is not the real question, maybe a discussion, I think, right? So I think that's very interesting, the topic. So I still want to maybe a discussion topic. So I think you, as you know, we can make for large optics, we can make a large interferometers, right? From like 24 inches, to 32 or maybe more. I don't know, but worldwide right now, I have never heard the 40-inch large aperture interferometer yet so far. But this is one direction. We can make a large aperture interferometer. But another directions, we can use the stitching technique, right? We can use so many the different sub apertures and stitching them together so that we can get a large the surface shape of the large optics. But I think we still have some limitations. For example, if you have right now you have the 4 meters, it's huge. It's so big, the mirror. But if you next day maybe you can make 8 meters, the large optics. So if you're still using the stitching, then maybe we have to think about it. What is a stitching arrow? And there's so many sub apertures stitched together, the stitching arrows. For large optics, we have to think about the cost, right? So my question is, should we also think, the two scientists? The one is called the Rich, another one is a Common, right? So both they develop a new method we call the Rich Common testing, right? So do you think we can maybe someday can use the Rich Common method or technique by using with the help of a normal or regular size of the interferometer. For example, we can just use the 4-inch, 4 inches aperture size interferometer to measure a large optics, like a 1 meter, 2 meter, 3 meter, or maybe larger. So that maybe is another direction we can think about it. Or have you ever used this idea, or have you never heard something about that? So that's just this discussion topic.
Well, this is it's really difficult to measure the large flight. If you are measuring optics, if you like me ranking the difficulties, I should say the most difficult one is a large flight.
Yeah.
Then is the convex A-sphere. Then is the concave A-sphere. Because for concave A-sphere, they can be tested by using a 4 inches interferometer, because the mirrors and the concave, when the light propagate is only expand, they can cover as large as they can. Right. So this is not a problem. But for large flight mirror, you need a large flight reference. So large flight reference is what you mentioned. They could be finished by using a Ricci-Kalman test. So one sphere together with this mirror under test. Then you can use the small pieces of reference to stitch them together. I think stitching is most important technique for large flight test. Because we are working on this for many years. We found the stitching technique is very promising and potential for the future aspherical, convex aspherical and large mirror, flight mirror measurement. We also are working on a 1/2 meter Fizeau reference. That one will work together with the stitching stage that can help us to test 4 meter flight, and also expandable to 6 meter or 8 meter. So very promising and potential technique, I think.
Okay, Professor Chair, so I think I'm done. Thank you for your introduction, and thank you, Professor Zhang, for your great talk again. Thank you, everyone.
Thank you. Thank you. I think that's actually one question in the chat, but I think that our time is approximately the time. And I must say, as people working on bi-imaging side, we are looking at very small things, but I'm really amazed to see how big optics you guys can make. And I surely will know next time when we want to make something, where should we go actually?
Okay, you got your optics.
So, okay. So let me just share again the slides. First, I will thank everyone. Thank Professor Han Shen and Fu Lan and Shen Hua for your participation, and also Professor Zhang for your wonderful talk. And here's a recap, outro. So a little commercial here. So when you guys want to make some ultra precision optical components, we all know where we should go. Okay, so this ends today's talk, volume 74. And next week we are going to have another group of wonderful speakers and panelists talking about another exciting cutting edge field about nanoplasmonics, from enhanced Raman spectroscopy and chemical reaction to optical tweeters of molecular. So next week we dive into small molecular again. So we switching between very big and very small one. And the speaker is Professor Tian Zhongqun, and the moderator is Nicholas Fang from MIT, and wonderful panelist. And also a reminder that ICANX is now the worldwide inviting young scientists to apply for this Young Scientist Award, which the deadline is in about a week. So for the young scientists, including the ex-channelist, channeler, we encourage you to submit your material. And we are going to have the Grand ICANX summit in Hainan Island at end of this year, December 19th and 21, and near the beach. On the beach, we will have science. That's very exciting. And with that, I'm going to close today's seminar here, and thank everyone for listening and participation. Thank you.